Stop the video for the matching answers. I'm going to focus on the delta V needed to get the Saturn V, the Apollo spacecraft into low Earth orbit at 330 kilometers above MSL. So we'll use V squared equals GM over R, or the velocity is the square root of GM over R, and I'll use a personal computer scientific calculator to show you how you might want to do that if you have one of these. First, you want to enter GM, and what I do is I use the 10 to the x power with 14, and then multiply that by 4, and that gives me G, and then GM, and then I want to divide. So I'll use the parentheses. I'll divide by R, which is going to be 10 to the 6th times 6.7 meters. And 6.7 equals the radius of the Earth plus the radius of the orbit. So when you get that, you'll compute that, and that'll give you V squared in meters squared per second squared. Take the square root of that, and then you'll end up with 7,726 meters per second, or 7.7 kilometers per second. That's your delta V that you need to get into low Earth orbit. Now the period of that, we'll just this is a circular orbit. We're just going to use 2 pi times the radius or the circumference over the velocity. So we know the velocity times the period equals the circumference. So I'm just multiplying 2 pi r, where r is 6.7 kilometers, and that gives us a period of 90.8 minutes. 90.8 minutes. Final question is to get the exhaust velocity of the rocket. We have to go back to Tsiolkovsky and compute the delta V, which I stored in memory, divided by 5,000, which is the exhaust velocity of the rocket, and that's going to give us 1.54. I'll go to the dV ratio chart. 1.54 gives me 5 for mass ratio 1/5. So 1 minus 1/5 is 80% fuel, or 20% payload. And that's it. And good luck.